So here, I'm going to talk a lot about physics, and I do apologize if it becomes a little bit technical, and I do not mind if you interrupt me with questions, or I can go until the end and you ask questions afterwards, but I'll try and give the technicalities together with some discussions that are kind of more conceptual, so that even if you don't follow the technicalities, you follow the conceptual and vice versa. So let's see. So the overview basically is like, these are the questions that kind of like got me interested in what I will talk about, which is, the first question was, is entanglement uniquely quantum? And I'm in classical optics. I was encountering a lot of instances of entanglement. And so that was one question. And then, can Bell's theorem be violated beyond the laboratory conditions in which quantum effects are expected to be observable? And these questions led me actually to the framework of causal modeling, which I mostly learned collaborating with Jacques Pinard, who unfortunately can't be here today, but was going to talk about general probabilistic theories. I'm very new to this work. You know, I've been working on this for about 3 years, but I found it a little interesting, and I thought it might be useful for you. So the topic of quantum entanglement, when I go to Wikipedia, right, and you say, wow, entanglement is at the heart of the disparity between classical and quantum physics. Entanglement is a primary feature of quantum mechanics, lacking in classical mechanics. And so you see, Wikipedia already like is a place where a lot of people go when they have a question of quantum entanglement. And the first thing basically that you have this idea is that it's this kind of thing that isn't, that is kind of distinguishing quantum theory from everything else. And I find it difficult to really pinpoint exactly what quantum entanglement is. And I'm not the only one. So there's been a lot of discussion in my field, in optics, classical and quantum optics, about the word entanglement. And there's even this opinion piece, this perspective piece by these scientists in Science saying, you know, the term entanglement has come to be used in a more general context, including single particle entanglement and classical entanglement. We do not endorse this nomenclature. So it's like the quantum physicists, some are on this kind of battle to define what is quantum entanglement in separation, or differently from other kinds of where entanglement can appear in other contexts, as if it were like holding a flag and, you know, I have to hold my ground. And I definitely don't think like that. So Catherine and I have been trying to understand where entanglement comes up, you know, in different contexts. And the more we try to pinpoint stuff, the more difficult it becomes for us to understand what is it that these physicists in general are trying to hold on to. Why is this term so dear and so different in quantum than it is in other things? And the basic thing when I think about this is, well, entanglement is nothing but, you know, in non-separability in a sense. So if you have any system and you can model it as in a Hilbert space, and for example, you can get, I'll give it one example. So you get a system and you can model it in a two-part, like as a vector in a Hilbert space, HA tensor HB. So you can just model it as a vector. Can you write this vector as a vector in the Hilbert space A, tensor product with a vector in Hilbert space B? If you can, it's separable. If you can't, it's non-separable. And this is a very technical definition of entanglement. But basically, this could be a definition of entanglement. And this has nothing to do with quantum. I mean, I can write quantum systems in a Hilbert space and I can represent them with vectors. But not only quantum systems, I mean, many other systems I can write in this way. And then in that case, is entanglement, why, you know, entanglement would not necessarily be a quantum thing at all, just something about how you can write vectors and model things as vectors in Hilbert spaces, and how these vectors can be factorized. And this was, in fact, part of this discussion between Einstein and Bohr. I mean, what are the implications of this non-factorizability in the case of quantum states? But Bohr was also interested in like implications beyond quantum systems. And it's like we can go on, and Catherine and I have been working on trying to write a paper on this on like for more than a year, and we don't. It's you can go on and on and on with this discussion. It seems to not really get anywhere, and I think that that's why we always end up falling back into Bell's theorem. So Bell basically, John Bell, in the 60s, got this discussion about what quantum entanglement means for, you know, what this non-separability means for quantum physics, or for classical physics, or for science in general. And the main thing that I think is essential here is that he says, well, let's frame this in terms of statistical implications. So let's abstract away from states on a Hilbert space and vectors, etc. And let's look, what are the statistical implications of this non-separability or entanglement? So basically, that's when we start seeing entanglement as a kind of correlation, right? And I think that this kind of gives an operational meaning, right, to entanglement, and we kind of it puts the whole discussion in a completely different framework, where I'm not discussing anymore about if I can model things in Hilbert spaces or not, if they're separable or not, but I'm looking at inputs and outputs, and somebody mentioned this in one of their questions. I'm just looking at inputs and outputs, and I'm looking at correlations between outputs given certain inputs to, you know, a system, and it doesn't really matter what my system is. I'm not modeling what's going on inside. So in other words, it's kind of a black box. I like, so I just want to read, you know, because I love this part. So Bell starts, you know, this paper on Bertelsmann stocks and nature of reality starts, the philosopher in the street who has not suffered a course in quantum mechanics, I love that, not suffered a course in quantum mechanics, is quite unimpressed by Einstein-Podolsky-Rosen correlations. He can point out to many examples of similar correlations in everyday life. The case of Bertelsmann socks is often cited. Dr. Bertelsmann likes to wear two socks of different colors. Which color he will have on a given foot on a given day is quite unpredictable. But when you see figure 1, that the first sock is pink, you can already be sure that the second sock will not be pink. Observation of the first and experience of Bertelsmann gives immediate information about the second. There is no accounting for tastes, but apart from that, there is no mystery here. And is not the EPR business just the same thing? In other words, is not the entanglement or non-separability of quantum states just the same kind of conundrum? And this is so important, this framing of entanglement in terms of statistical correlations, that if you look at the citations of the Einstein-Podolsky-Rosen paper, in which they kind of question, the completeness of quantum theory based on the possibility of there being entanglement, right? The citation of this is not very much in the field in the first 30 years, but after Bell published this, then these papers started to be cited much more. In other words, kind of the philosophical debate around entanglement kind of was to a different level, and was able to, because Bell made it possible for us to actually do experiments and tests and discuss entanglement in the framework of probability theory. And today, this paper of Einstein, which he in fact didn't really like that much, and he had a fight with Rosen about it, is today Einstein's most cited paper, which I found a bit strange to find out. But I think all of this is because of quantum information theory, because in fact, Bell's theorem is the bread and butter of quantum information theory. In quantum information, which is the basis of quantum computation, quantum computing, basically most of the quantum technologies that people are talking about right now, quantum internet, etc. The formulation which people mostly use is not states in Hilbert spaces, but what they call device-independent formulation of quantum phenomena. And that basically only refers to probabilities, inputs and outputs of black boxes, and correlations between these outputs. And so we kind of like this Bell, from Bell to quantum information and quantum computation, etc., etc., etc. We don't really see in this literature as much the Hilbert space formulation and the discussion of entanglement in terms of non-separability as much as we see entanglement appearing as something that is responsible, or that explains certain strange probabilistic outcomes that we get from, statistical outcomes we get from experiments that we do with electrons and photons, etc., and that we can apply for even, to quantum computing, etc., etc. So a typical, let me go through like a very typical Bell test scenario for those who've never heard of it. So we usually have, a source, and that can be, I don't need to know, again, this is in device independence means I don't have to know much about this source. It can be producing, cakes, it can be producing balls, it can be producing electrons, photons, it doesn't really matter. What matters is I have a source, and I have a person on, a system, Alice, it can be a person, an AI, whatever, on one side, another person, AI, on the other side. I think I'd argue it has to be a person, but we can talk about this later. And they have a dial or some measurement apparatus, and again, it doesn't really matter what this measurement apparatus looks like, if it's a photon counter, if it's it doesn't really matter what it looks like, if it's somebody eating a cake. What matters is that they can have different settings. They can choose 2 different settings, or 3 different settings, or n different settings on this apparatus, and they will have different outcomes that they will record for each setting, and then they'll come together and they'll discuss and compare their results. So again, so I have Alice and Bob, and they're each kind of like choosing, oh, I'm going to choose setting 1, setting 2 on my dial, on my device, and I've got this outcome or that outcome, and I'm going to write each of these outcomes down with the setting that I chose, and then I'll come together with Bob and we'll discuss and we'll compare our results. And basically, I'm going to look for correlations between my results and his results. So here we have an example where we have, which is most typical case, but isn't the only case, where you have 2 possible settings and 2 possible outcomes for Alice and Bob's measurements. But really, this can be, n. We don't, a Bell test isn't only for 2 settings and 2 outcomes. But the important thing is that in this formulation, we associate a random variable to the measurement settings and random variable to the measurement outcomes that each of them can obtain. So, and then we compare their outputs. So you know, what Alice got depending on her setting and Bob got depending on his setting for each experimental run. So we're all kind of, we're going to compare experimental run 1, 2, 3, 4, 5, you know, I don't know, n experimental runs, and we're gonna look, see if we can apply the assumptions of Bell's theorem. So the assumptions are the typical assumptions formulated in usual way. Is local causality. So the first one, is there or are there any direct causes between the outputs? So I'm saying that if there are, so if there's no, if Alice can't, if Alice's outcomes can't cause Bob's outcomes, for example, in a typical Bell test scenario, these will be space-like separated. So we guarantee that that is the case, but it could be another situation. So if there are no direct causes between the outputs, then any correlations will be due to a common cause. And another part of local causality is that Alice's measurement doesn't affect Bob's outcome and vice versa. So again, in a typical Bell scenario, these will be space-like separated. So we guarantee that the outcomes from one side of the other cannot affect each other, and that the settings of one side cannot affect the settings of the other. And these are what we can call local causality. But it needn't be so. We needn't have space-like separation. We can have other conditions that don't allow them to cause. For example, these could be, you know, questions to people, to two different questions I make to a person, two different questions I make to other people on this side, and I just guarantee that they can't talk to each other, for example. And then the second thing is measurement independence. The measurement settings chosen by Alice and by Bob are independent from each other and from the source. So basically Alice can at each run chooses randomly which measurement to make. So the dial on her apparatus, and Bob does the same, and they're not they haven't decided together, or the source doesn't tell them which setting to use. So they've got like, that's also like free will could be another way to say that. And then you given those assumptions, you divide the statistical inequality and you test if the observed correlations between Bob's and Alice's outcomes, given their settings, in other words, conditioned on their settings, can be explained by a locally causal theory with measurement setting independence. This is what usually like Bell formulation gives. Locally causal just means that the theory that these two conditions are met, and with measurement setting dependence means that this condition is met. So this is very kind of technical, and what does it mean really? It's very difficult to grasp kind of the meaning of this, I think, in a kind of general case. And in fact, when you go beyond quantum theory, for example, what got me interested in the stuff I'll talk about was classic, you know, lasers violating. Lasers in optics are considered non-quantum for this case. And so non-quantum systems in physics were violating Bell's inequalities. And I wanted to understand, like, what's the meaning of this in this context? Because we talk about the meaning of Bell inequality violations in context of, you know, of electrons and photons, and it seems very profound. You know, we have a non-local, you know, or non-local causal theory, or, you know, things that sound very profound, and you keep thinking, but what does that mean? You know, and there's lots of interpretations. Is it causal? Is it not causal? And I said, well, what does it mean elsewhere? You know, if we don't know what it means in quantum mechanics, do we know what it means in other, like, classical optics? Do we know what it means when we violate Bell's inequalities with human behavior, cognition, economics, etc., etc.? So this kind of test, can be used far outside the laboratory conditions in which quantum effects are expected to be observable. And the question is, I mean, as we've been discussing, I mean, the interpretations of this everywhere are a bit, are really not understood. And this makes me really kind of like bring home this point, because we have the violation of Bell's inequalities in many of these situations. And but the question is, do we have violations of Bell's theorem? And what are the implications if we do and if not? So a violation of Bell inequality is only as meaningful as the physical assumptions used to derive that inequality. These assumptions can be very different in different experimental setups. So what it means to violate a Bell inequality can be very different in different experimental setups. And the experimental violation of Bell inequality with different sets of assumptions can actually even mean nothing at all. So I've seen somewhere Bell inequality violation with a rubber band, and I'll explain why. But this means nothing at all, because the rubber band scenario, if you have a rubber band and I'm pulling from one side, pulling from other side, it doesn't, I can't apply the assumptions of Bell's theorem. Going back, these would be the assumptions of Bell's theorem in the way that the kind of Bell put it. So this kind of led me to this thing, to causal modeling framework, which is something that Jacques Pinard has been working on for quite a while, and him and a few other people started applying this framework to quantum systems to understand the implications of quantum systems within this quantum Bell violations within this framework of causality. I found that very interesting, and I thought, can we apply this elsewhere? So I'm going to present kind of this here to you. So the idea of causal modeling is to derive Bell inequalities from assumptions of the system's underlying causal structure. So I'm going to give a brief introduction. I'm going to stop talking about Bell for a little bit and give a brief introduction to causal modeling, and then I'll put causal modeling and Bell inequality violations together, and I'll go to kind of a different set. It's a different way to formulate Bell inequalities and Bell's theorem that might give us some insight as to the meaning of this in quantum physics and outside quantum physics, or maybe not, but it could be something that's interesting to you. And so let's see. So causal models were developed and basically by Janeiro, and my mother's epidemiologist, and usually nobody knows what an epidemiologist is, but because we have COVID now, everybody knows what an epidemiologist is. And she's been working with causal modeling since a long time. And in epidemiology, it's the basic framework in which they find models of causality. For example, she told me that the fact that smoking causes cancer, like that. So for a long time, people have seen correlations between smoking and cancer, right? For a long time. But to say that smoking causes cancer is a completely different thing than to say that smoking and cancer are correlated. For example, if I say that smoking and cancer are correlated, means that in people, there's a correlation between, it can mean that either people, for example, people who smoke and people who have cancer, it's kind of the same genetic predisposition to smoking and to having cancer. That could be an argument that I could give you to justify smoking and cancer having a correlation. So that would be a great argument for example, for example, if I have I'm Marlboro could give that argument saying, oh, just because the doctors are finding a correlation in the hospitals between smoking and cancer doesn't mean that smoking causes cancer. So continue buying our cigarettes because it's just a genetic predisposition you have to smoking is the same one that you have to cancer, and one has really nothing to do with the other. But a completely different thing was when they were able to use this causal modeling to prove that actually cancer, that smoking causes cancer. And that is a completely different thing, because then if I'm selling Marlboro, I have to say, and I have to put it on the back of my cigarettes, that if you smoke, this fact, together with other genetic conditions, etc., but this fact in itself is a cause. It's not the only cause, but it's a cause of cancer. And that changes the whole public health issue around smoking and cancer. Why am I saying this? Because this framework developed by Janeiro for engineering, applied to epidemiology, completely transformed the field of epidemiology and public health. And this is where my mom works, for example. She's a scientist in that field. And then, and it's used a lot also in computer science. And in the case of quantum physics, it's very recent. And it really can change the way we think also about quantum physics. So I'm trying to give you kind of the idea of this, the fact that like this framework is powerful for many different settings. So I look at correlations, and I have correlations between X and Y, for example, and these are two random variables. So it can be, for example, smoking and cancer. So again, Reichenbach's common cause principle says that any correlations between X and Y can only be due to one of the following conditions. Either X causes Y, smoking causes cancer, or cancer causes smoking, for example, that could be another option. A common cause, for example, both of them, you have a genetic predisposition that makes you want to smoke and gives you cancer. That's another option. Or you have a combination of the two. You have smoking causes cancer and there's a genetic predisposition that makes you want to smoke and makes you have cancer, for example. So any correlation between random variables X and Y can always be framed in this way. This is in Reichenbach's principle. Either one is direct cause of the other, they both have a common cause, or they have a combination of these two. So if there's an implication of this, that if two variables are correlated but neither can signal to the other, they must share a common cause. What does that mean? That means that if I get smoking and cancer, for example, right, and I get a group of people and I force half of them to smoke and I force half of them to abstain from smoking, right? Can I still see a correlation between smoking and cancer? If I still see a correlation between smoking and cancer, that means that there is a common cause between smoking and cancer. But if I do this, I force half of the population to smoke, and I make the other part of the population, I make them abstain from smoking, and they lose that correlation, then it must be that one of these, either cancer causes smoking or smoking causes cancer. Why is this important to us? We'll see. Another thing in causal modeling is that if two variables are uncorrelated, that means if smoking and cancer are uncorrelated, they cannot be causally connected, either as a cause effect or by common cause. For example, blue eyes and smoking. So they are uncorrelated, right? And that means that there's not a common cause, genetic or otherwise, that causes people to have cancer and blue eyes. And also blue eyes don't cause cancer and cancer doesn't cause blue eyes. So this is called no fine tuning, which means that if there are no conspiratorial fine tuning that makes correlations disappear, if there are causal links between variables X and Y, they have to show up in the statistics. If I don't see correlations in the statistics, there's no causal connection between those two things. This is really important because otherwise I could say there's hidden hidden causes and that actually do, you know, cause people to have blue eyes and cancer, but I'm not seeing them in statistics, so I wouldn't be able to model that. So this is essential for modeling, actually. And then you use something called the causal Markov condition, which is a tool that allows me to derive statistical inequalities, not just Bell inequalities, any statistical inequalities from any given causal structure. So, for example, from any, so if I have correlations and I have assumptions about what can be cause of another thing, then I can find statistical inequalities concerning those correlations for X and Y from those assumptions about the causal connections between X and Y. But there's one thing that is important. So if you have, going back to Bell inequality violation, if you get the statistics observed in any Bell inequality violation, be it with electrons, be it with photons, it doesn't matter, be it with human beings, if I get the statistics observed and they violate a Bell inequality, right? And I try to make a causal model for that, which takes into account Reichenbach's principle, common cause principle, the known fine-tuning principle, and the fact that Alice and Bob can't influence each other's measurement settings and can't influence each other's outcomes, then there is a contradiction. These things together do not work out. There's something wrong. You cannot have all of these things together. In another way, in other words, if you have a statistical observation in Bell inequality, you have to, the other things has to be given up for you not to fall into contradiction. And this is a lesson from causal modeling framework. So in this framework, let's reframe Bell's theorem in causal modeling framework. So if there are no direct causes between X and Y, for example, then any correlations are due to common cause. So we've talked about that. That's Reichenbach's common cause principle. So there must be a cause that is a cause of X and a cause of Y. If X doesn't cause Y and Y doesn't cause X, although X and Y are correlated. So I'm assuming in Bell's theorem, whenever I apply Bell's theorem, I assume that there's no cause between X and Y and X. In the case of Bell's inequality, how he formulated it, that meant he put space-like separation between Alice and Bob, and that would theoretically guarantee that you have no direct causes between X and Y, for example. But you can have other ways to guarantee that. The other one is no signaling. Again, Alice's setting A doesn't affect Bob's outcome, and Bob's setting B doesn't affect Alice's outcome X. So this is called no signaling. So now in Bell's theorem, in the causal modeling framework, these are two essential conditions, which is a reformulation of those conditions that he calls local causality. So here there's these two, 1 and 2 together would be what Bell called local causality, but now in a different, more general kind of setting here, okay? Because I'm not making any assumption about the source or anything. And the measurement setting independence, A and B are independent from each other and from lambda. So there's no causal connection between A and B. So A doesn't cause B, B doesn't cause A, and lambda doesn't cause A, and lambda doesn't cause B. This is super essential. Also connection to the. So this is called a DAG. So this is my assumption. I have outputs of the experiment, Bell's experiment. They have a common cause, which is the source, and can have hidden variables, whatever you want in here, doesn't matter. And another cause of them are each of their settings, A and B, A on Alice's side and B on Bob's side. And this is the graph that tells me what everything I've set up to now, all these assumptions. And together, I can use causal Markov condition and derive this. This is a condition on the probabilities of X, Y conditioned on A, B. The probabilities of the outcomes conditioned on the settings. That's this one thing implies the other. And this equation implies a set of statistical inequalities. A set, not one, but a set of statistical inequalities. If any of these inequalities are violated, then the causal graph cannot explain these correlations. In other words, if I derive an inequality, I publish a paper in that because it's very difficult to find the statistical inequalities given this equation. But if I do find one, I publish a paper, and then we do an experiment that violates this inequality. That means that this causal graph, in other words, these assumptions, cannot explain the correlations I saw between outcomes of Alice and Bob given the settings of Alice and Bob. A very common, a very kind of famous instance of this is the Clauser-Hom-Shimony-Holt inequality, which is when these random variables have two possible outcomes. And so each outcome is a random variable with two possible values. And each setting of Alice and Bob is a random variable with two possible outcomes too. And in that case, this is a famous CH-SH inequality, which they derived a long time ago and has been tested numerous times with electron spins, with photon polarization, with atoms, with all sorts of things. And this is an inequality which says, right? So this S is a variable which depends on all these probabilities of the different outcomes given different settings. And I put them together in a certain way that has, if I sum all of these M's, it doesn't really matter how I get here. The important thing is that it gives me, I have to measure all of these probabilities, and if I get an outcome, this sum is smaller than 2, then this causal graph does explain the statistics I observed. If this number is larger than 2, then this causal graph does not explain the correlations between X and Y. Notice that I made very few assumptions about lambda. I don't care what it is, you know, what the source is, if there's hidden variables, I don't care. All I'm saying is this graph, these causal connections can only explain the statistics if this number S, which is formulated with the probabilities of certain outcomes for certain settings, is smaller than 2. But we know that some quantum entangled states, not all quantum entangled states, can violate CH-SH and other Bell inequalities. This is a very important point. People think that entanglement and Bell inequality violation is the same thing. Not all states that can be written as a non-separable system like this can violate a Bell inequality. There are states that cannot be written as a separable system, but cannot violate a Bell inequality. And in the case of the CH-SH, the maximum violation of Bell inequalities is with quantum states that look like this, or whatever states. These don't have to be quantum. Again, I can be modeling anything that I can model in a Hilbert space with vectors, and if I write it like this, then this thing will violate the Bell inequality. And there's a maximum violation when I write things in this way, and it's called the Tyrrellson bound, the quantum maximum violation. But this isn't the maximum value of S that can be had with any probabilistic model. Actually, general probabilistic models, which is what Jacques was going to talk about in his talk, they can violate, they can give S up to 4. So you have a regime here of things that can violate, can have S. So you do a CH-SH scenario, and you get this value S, and S is larger than 2 square root of 2. Then you know that this model that I'm showing you here, this Hilbert space with these vectors and the quantum probabilistic structure, is not going to be good to explain your outcomes either. So this causal model is no good for you, but also this model is no good for you if your S is larger than 2 square root of 2. And all Bell inequalities will have a violation, a quantum bound. There's a classical bound, which is the low one, there's a quantum bound, and then there's another bound which is for general probabilistic theory. So this is another interesting thing to keep in mind, that it's not just because you violated a Bell inequality that your quantum formalism can be a good way to model your system, right? So some entangled quantum states can violate Bell inequalities, which means that this causal model does not explain it, and the probability distribution of P of the outcomes X and Y given AB is outside of a set of correlations produced by a common cause. I've heard this so many times that people think that because entanglement is a correlation, then it is explained by a common cause. Exactly the contrary. Entanglement cannot be explained by a common cause. So a lot of people in physics and out of physics say, oh no, entanglement is no correlation. Yeah, no, it's not. Entanglement is a correlation that cannot be explained by a common cause. This is an important point to put out there again. So again, the statistics observed in Bell inequality violation plus the assumptions of causal modeling, Reichenbach's common cause principle, and no fine tuning, knowing that Alice and Bob's sides are kind of separated, they can't send signals to each other, leads to a contradiction. And this is what we learn from quantum modeling. So when we see a violation of a Bell's inequality, right, we have to ask ourselves, the first thing is, so I'm not making any assumption about what it is inside, what you're doing, if you're using economics, it doesn't matter. I see correlations. I violate a Bell's inequality. And so the first question you ask is, does the experiment satisfy the assumptions of Bell's theorem? In particular, can we guarantee that one side isn't sending signals to the other side? So there's no signaling from the measurement settings to one side and the measurement settings on the other side. And can you guarantee that each side is free to choose their measurement settings randomly and independently of each other and independently of a source way back when? If you cannot guarantee these things, then the Bell inequality violation has no profound implications at all. So it doesn't matter. If you say yes to these things, then there's something that is profound and you can start thinking about. And then we can go various routes. So we can talk like Bell's, the traditional way of thinking it. Do we have to give up local causality? Not. Is this a non-local theory? Is it not? All these discussions. Do we have to reject measurement setting dependence? Like, do we have to have superdeterminism? These are all discussions that have been out there for many, many years. Or in the more general framework of causal modeling, your decisions are different. They are, do we have to reformulate Reichenbach's common cause principle? Do we have to reject no fine tuning? And do we have to reformulate the causal Markov condition, which is a quantitative probabilistic conditions that you put on the statistics? Or do you give up on the do you completely reform? In other words, do you completely reformulate these conditions, or do you reformulate also probability theory? That's another option. Or there's another way that you can another way to frame Bell's inequalities, which Krenikov talked about a little bit, which is contextuality. And again, it's more general than the usual kind of the Bell inequality formulation, the traditional one, but it's a different one from causal modeling. So it gives you another set of things that you have to choose. And for example, Wood and Speckens, there's a very important, this is the most important paper in this causal discovery algorithm for quantum correlations, they decide that they cannot reformulate Reichenbach's common cause principle, they cannot reformulate causal Markov condition, so they reject fine-tuning. I didn't put here, but Jacques Pinard has another has a work where he says, well, I don't want to reject no fine-tuning, I don't want to reject the Reichenbach's common cause principle, I'm going to reformulate the Markov condition. So different authors will choose different ways to solve this contradiction. And just to finish, an epilogue. A lot of people come who are in and out of quantum physics like to talk about the wave-particle duality as another thing that's only quantum, and that, you know, quantum physics is different from classical physics. And so there's always a story of the double slit, and if there's interference on the screen, then that's a wave model, and if there's no interference on the screen, it's a particle model. And in quantum mechanics, you have a wave-particle model. Okay. And even more so, there's Wheeler's delayed choice experiment and quantum eraser experiments, where you can decide if you are going to get a so you can change your double slit setting by putting an observer, way to observe which slit each electron went through, if you'd like to talk like that or not. And then your interference pattern will appear or disappear after the electron has already left the electron gun beam. A way to talk about this would be, that I hear people talking about it, is, so there's an electron that leaves the beam and it has to decide if it's going to act as a wave or a particle. And you decide, yeah, and you change, you try to fool it by changing your experimental setting last minute after it's already left its thing, and you try to see if you can fool it and have it give a different result than it would have given if you hadn't tried to fool it. So these are called the Wheeler's delayed choice experiments. So you decide if you're going to test the wave nature or the particle nature of an electron after the electron has been, is kind of like midway through air, and so this would be kind of like, wow. So the fact that the electron doesn't have a wave or a particle character intrinsically before you decide what to measure means that this is a very strange thing, and that quantum mechanics is very weird, and we have to rethink our whole lives. This is something that always comes about, and we have long debates between Einstein and Bohr. But again, I say let's think of, remember that quantum mechanics only gives statistical predictions. So let's abstract away from thinking of each electron as, you know, a flying wave function, and try to give, you know, meaning to that wave function. Let's think about the statistical predictions, because having or not having interference pattern is not a characteristic of each electron. It's a characteristic when you have many electrons going through the experiment and you accumulate the results. So it's statistical. It's a correlation between what you see at the output on the screen and what measurement setting you have chosen. That's another way to think of it, a way of a statistical prediction, which, so we don't have to think of each electron and try to make, you know, a lot of philosophical discussions about what the electron is thinking and doing, etc., etc. And oh, I put this in, sorry, in Portuguese. The Wheeler's delayed choice experiment is often considered either a proof of retrocausal effects. In other words, because I choose later if the electron is going to have to display wave or particle statistics, then it's like I'd have to, like, the electron would have to kind of, that would cause the electron to come out as a wave or a particle from the beam gun. So that's a retrocausal back in time. So when I chose that, then it causes back in time the electron to decide if it's going to be a particle or wave. And it's also often called, often in literature you see it as a proof that one can't attribute objective reality to the properties of a photon or electron, etc. In other words, that the photon or the electron cannot be a particle or a wave when it leaves the source. I'm saying, let's not think about it this way. Let's ask, assuming no retrocausality, is it possible to obtain the statistical results of Wheeler's delayed choice experiment or any interference experiment in quantum mechanics by attributing objective realities to the properties of each photon, or better still, by assuming hidden variables? And yes, the Wheeler's delayed choice experiment, including quantum erasers and any quantum interference experiment in like a double slit or interferometer, can be explained by a classical causal model. So this is a different way to formulate. In the causal modeling framework, we can find a causal model. And so in this framework, wave-particle duality is not strange at all. It's not something like, in this framework, it's not something that makes quantum mechanics strange. The only thing that makes quantum mechanics strange in this formulation that we know of is violation of Bell inequalities. And wave-particle duality kind of falls out of the picture in this formulation. And this is something that I find interesting to tell people both in physics and outside of physics, that if you look at it from this general framework, then yes, I can have causal models of the type that we use to explain how, smoking causes cancer, or how, my COVID can affect my husband's COVID. And I can use that same kind of causal modeling framework to describe the interference of double slit experiments, to describe Wheeler's delayed choice experiments and quantum erasers. So I find that curious to put out there. And this is work that we published a few years back. And so, closing it all, violation of Bell's inequalities plus classical causal modeling is a contradiction. Double slit experiments and quantum erasers can be described by classical causal models. And causal models, not all, we actually devise an idea of a delayed choice experiment that can't be described by classical causal model when you have assumptions about the source, by the way. And causal models can be an interesting framework to analyze quantum-like phenomena. So thank you very much.